The core challenge in data science is often finding a mathematical model that perfectly aligns with real-world observations. Today, we are dealing with a highly rigid structure, a fifth-degree polynomial curve. To lock this exact curve into place, we need to solve for one completely unknown constant, a parameter we will call c. This graph shows the 4 points our curve must fit: 0, 0, 1, -4, 2, -7, and 3, 151. Since c is a constant, altering its value shifts the entire structure up and down the y-axis, while its underlying shape remains exactly the same. The standard modern approach to finding the optimal value for this parameter involves applying calculus or writing a script to computationally brute force the answer. We are going to abandon calculus entirely. Instead, we will construct a purely geometric model of our system's error and reduce it into a solvable polynomial. Finding the perfect model is a matter of recognizing that geometric distance can be translated into a definitive algebraic structure. Polynomials are rigid geometric structures, governed by strict rules. When complex polynomial systems interact, their highest exponent, the degree, strictly dictates the ultimate shape. Here, we have a complex rational function, built from 3 polynomials, p, q, and r, with degrees of 2, 3, and 4. Multiplying polynomials causes their degrees to add. Substituting those values into the first term, p times q yields a degree of 2 plus 3, which is 5. Continuing across the numerator, q times r gives us 7, and r times p gives us 6. Because we are adding these terms together, the maximum degree, 7, dominates the entire top half of the function. Down in the denominator, adding the degrees of p and q reveals that the bottom half is dominated by a degree of 5. When one polynomial divides another, their dominant degrees subtract. Subtracting the denominator's 5 from the numerator's 7 leaves us with a final degree of 2. The large rational fraction collapses into a clean, simple parabola. No matter how complex a polynomial system appears on the surface, analyzing its degrees instantly reveals its underlying geometric behavior. We can apply that exact logic to our central challenge, locking in parameter c for our fifth-degree model. To do this, we force our theoretical equation to interact with our rigid, real-world data points, 0, 1, 2, and 3. Evaluating the function at x equals 0 instantly zeroes out the large exponents, leaving us with exactly c. At x equals 1, the arithmetic quickly simplifies to c minus 5. When we input 2, the large powers cancel each other out, 64 minus 64, simplifying the entire expression into c minus 6. As we input larger data points, the massive exponents generate huge integers that violently offset each other. For our final point at x equals 3, the resulting integers reduce all the way down to a compact expression of c plus 153. By feeding real-world constraints into an abstract system, we collapse fifth-degree complexity into 4 simple, linear expressions of our unknown parameter. In data science, error is the literal geometric distance between our theoretical model's output and the actual recorded data. To measure this total distance, we use the sum-squared error protocol. Squaring these distances penalizes large outliers and prevents negative and positive deviations from canceling each other out. Let's calculate those squared differences. For the first 2 points, subtracting the target y values leaves us with c squared and c minus 1 squared. Subtracting the remaining targets yields c plus 1 squared and c plus 2 squared. Now we expand these binomials. By squaring these linear terms, we naturally elevate our entire error system into a quadratic degree. Expanding the terms reveals the raw polynomial components. Notice the positive and negative cross terms throughout the equation. The positive 2c and negative 2c cancel each other perfectly. The c squared terms sum to 4c squared, and the constant terms, 1, 1, and 4, accumulate into a final result, 4c squared plus 4c plus 6. The abstract, messy concept of total error across multiple data points has been perfectly distilled into a single, independent quadratic polynomial. We now have a master equation for our system's total error. E of c equals 4c squared plus 4c plus 6. Recall our earlier rule. The highest degree dictates the geometry. Since this polynomial is degree 2, its shape is strictly a parabola. This graph plots our total error against parameter c. Because the leading coefficient of 4 is positive, the parabola opens upward, meaning it possesses a single absolute lowest point. This lowest point is the vertex. In the strict context of our model, finding this coordinate gives us the absolute minimum possible error. To find it, we use the vertex formula, c equals negative b over 2a. We pull our b and a values directly from the polynomial, giving us negative 4 over 2 times 4. That gives us negative 4 divided by 8, which simplifies to exactly negative 0.5. We have mathematically proven that an error-minimizing fit occurs exactly when parameter c equals negative 0.5. We locked in this exact value without relying on a single derivative from calculus or running endless computational iterations. By understanding how polynomial systems combine, divide, and structure themselves geometrically, we can translate complex data-fitting constraints into a definitive algebraic proof.